From the book, here are some objectives from the C4 book. So recall some physical properties and chemical properties of groups 170. Explain the reactions of group 170 at zero lack of reactivity. Predict properties from given trends. Describe and explain displacement reactions involving halides and halogens. Recall the general properties of transition elements. Explain the different reactivity of metals. Put metals in order of reactivity. Predict reactions and reactivity of elements. Describe laboratory tests to detect oxygen, hydrogen, carbon dioxide, and chlorine gas. Describe and interpret flame tests. Describe hydroxide precipitate tests to identify metal ions. Detect anions. Use qualitative reagents, techniques, scientific instrumentation, interpretation of results. Right, so to detect hydrogen, you need a lit wooden splint to the test tube that's containing the gas, and then what you would hear is a squeaky pop sound. For the test for hydrogen, I mean the test for oxygen, you light a splint and blow it out. Ensure the splint is glowing. You put that inside the test tube or above it, and then the light will relight. The splint will relight. Carbon dioxide, this is for lime water, so you would bubble the gas through lime water. The lime water will have calcium hydroxide, and what is produced? A white precipitate of calcium carbonate. This is commonly referred to as the lime water going cloudy. Chlorine gas, you add damp litmus paper. Litmus paper is an indicator to determine whether something's alkaline or acidic. So it's just a strip of blue paper or red paper to determine whether something's alkali or acidic. So, for example, if something is acidic and you put blue litmus paper to that substance, then it will turn red. The litmus paper is bleached white. Metal hydroxide tests for positive ions when sodium hydroxide solution is added. So if you look at group 2 metals, calcium and magnesium, they are white. So group 2 metals, they will give a white precipitate, calcium, magnesium. Aluminium 3+ will be white, dissolves in excess sodium hydroxide. Now if you look at the transition metals, they are usually colored. So copper, the usual color is blue. For example, copper sulfate are blue, copper sulfate crystals are blue, so copper will give a blue precipitate. Iron 2+ will give a green precipitate. Brown if allowed to come into contact with air due to oxidation, and iron 3 is brown. The general trends for group 1 metals is that the density will increase, the general trend, apart from calcium. Is it calcium? It is potassium. So after sodium, potassium goes down and then it goes back up again for rubidium. For the melting point, it will decrease down the group. The general trend is that it will decrease down the group for alkali metals. How do you explain the trend in reactivity? Well, I'm just looking at the bottom part really. So the easier it is for an atom of a group 1 element to lose its outer electron, the more reactive it is. So because the electron is further away from the nucleus, it is more reactive because it wants to get rid of that extra electron. So for example, potassium is more reactive than lithium because its atoms lose their outer electron more easily than lithium atoms do. So that's the equation. When it loses the electron, the alkali metal atom becomes ionized because it's lost that electron. It gains a positive charge and the electron is removed from the atom. Right, this is a question. This question is about the elements in the periodic table. Look at the list of elements. You've got argon, hydrogen, magnesium, nitrogen, potassium, calcium, iodine, neon, oxygen, and sodium. Answer the questions. Choose your answers from the list. Each element can be used once, more than once, or not at all. The periodic table on the back page may help you. Unfortunately, there's no periodic table. You need to find the periodic table if you can. Right, so name the non-metal element, which is a grey solid at room temperature. Now this is a non-metal, so you can eliminate magnesium, potassium, calcium, and sodium. It is also grey solid, so you can eliminate the gases and liquids. So the gases in the list are argon, hydrogen, nitrogen, oxygen, neon. So the only thing that's left seems to be iodine, and that's the answer, is iodine. Which element has an atom which only have 5 electrons in its outer shell? Well, you need to look in the periodic table. Whichever element is in group 5, that is your answer. Write down the name of the element which has the electronic structure 2882. So because it has 4 shells, because it's got 4 numbers, 2882, it is in row number 4, and it will be in group 2 because it's got 2 electrons in the outer shell. That means that it is in row 4 and second column from the left. Here are your answers. Iodine, nitrogen, and calcium. It does say allow magnesium. Why does it say allow magnesium for B? Oh, right. No, that's not. That's not. I don't know why that is. Why would magnesium be? Right, yeah, I don't know why that says magnesium. I don't think it's magnesium because magnesium is in group 2 and it has 12 electrons. So that would be 282. Right, part C, the electronic structure is calcium. Right, this question is about group 1 elements such as sodium and rubidium. Look at the table, it shows some information about the elements in group 1. So there the table is, it's there. Group 1 elements such as sodium react with water. Sodium hydroxide, NaOH, and hydrogen are made. Write down the balanced symbol equation for the reaction between sodium and water. Part B. The reaction of rubidium with water is more violent than the reaction of sodium with water. Rubidium is more reactive than sodium. Explain why. Use idea about electrons. Alright, so the answer is 2Na plus 2H2O. That gives 2NaOH plus H2. 1 mark for the correct formulae, 1 mark for correct balancing. It is easier for rubidium to lose electrons when it reacts than for sodium to lose electrons because rubidium has a larger atomic radius. But that is because the electron is further away from the nucleus, and so therefore there's a weaker attraction. Yeah, I think it needs to say because the rubidium outer electron is further away compared with the sodium, and there's a weaker attraction between the nucleus and the outer electron. Right, describe and explain the relationship between atomic radii and melting points of the elements in group 1, including your answer predictions for the atomic radius and melting point of rubidium. Radii is just plural of radius. So there is the table with atomic symbols, numbers, melting points, densities, and atomic radius in picometers. PM stands for picometers, and pico is 10 to the power of minus 12. Alright, so the answer is... this is just to help you. How does the melting point change down the group? Why? How does it relate to the radius? What is a metallic bond? What about the forces between nucleus and electrons? Mention data. Right, so the answer is here. Relevant points include melting point decreases as atomic radius increases. Melting point decreases because it is easier to overcome the metallic bond, because strength of metallic bond decreases as atomic radius increases. Idea that metallic bond is the attraction between delocalized electrons and closely packed metal ions. Idea that atoms lose electrons more easily than the group 1 because the attraction is weaker. Melting point of rubidium is any value between 30 and 50. Atomic radius of rubidium is 272 to 295 picometers. This question is about the reaction of halogens with alkali metals. Astatine reacts with potassium. Construct the word equation for this reaction. So there it is. Potassium plus astatine gives you potassium acetatide. This is from a specimen paper. It does say allow, but why does it say word equation then if it allows a chemical equation? And it's not even balanced. So I don't know, but it should be potassium plus astatine gives you potassium acetatide. Right, question 5. River water needs to be purified before it can be used as drinking water. Look at the table. It shows the mass of different ions in 1 kilogram of river water. A. Kritika, a research chemist in a water purification factory, needs to know the percentage of lead ions in the water sample. What is the percentage by mass of lead ions, Pb2+, in the river water? So what is the percentage? There it is, the answer. And then for testing of sulfate ions, now to test for sulfate ions, you need to add dilute hydrochloric acid followed by barium chloride solution. A white precipitate of barium sulfate means the original compound was a sulfate. And the ionic equation is the following: Ba2 plus aqueous plus the sulfate ion, which is 2 minus aqueous, that gives you BaSO4. Now, because the sulfate ion has a charge of 2 minus, the barium has a charge of 2 plus, what they do is that they will naturally combine together, producing BaSO4, because the 2 minus balances out the 2 plus. Also, if you look at this, barium is at the bottom, quite close to the bottom of group 2. So you can see that barium is one of the most reactive group 2 metals. And that's why it would react with the sulfate ion, the 2 minus. So, this is in the book, the OCR C4 book. Barium ions react with sulfate ions to produce white insoluble barium sulfate. You've got Ba2 plus aqueous plus sulfate ions, SO4 2 minus aqueous. That gives you BaSO4 solid. This forms the basis of a simple laboratory test to detect sulfate ions in a solution. So you add a few drops of dilute hydrochloric acid, then add a few drops of barium chloride solution, BaCl2. If sulfate ions are present, you get a white precipitate. Okay, that will help you in the next question. So the river water is treated in the water purification factory, suggests why the tap water the factory makes may still contain lead ions. Part B, Kritika tests a sample of the polluted river water with barium chloride solution. Predict what Kritika would observe and explain why. Right, so the answers are coming up next. Purification methods do not remove soluble impurities, and the lead ions may be in solution. Lead ions may come from old lead pipes. Part B, white precipitate, because barium sulfate is produced, which is insoluble due to the presence of sulfate ions. Right. Now the one at the top was the one that was given to you earlier. The one on the bottom right was also in the book, but the thing is, I removed the third column. This was on Wednesday's slide, so I removed the third column because that is exactly the same as the top left. If you can see the top left and the bottom right, I mean, all it says is just no precipitate. But if you look at iron 2, that will make a green color precipitate when you add hydroxide. So iron 2 is green, iron 3 is orange brown, copper 2 is blue, and calcium zinc are white. So and calcium is white, magnesium is not in the I'm looking at the bottom left. Aluminium is not there, but copper is there, iron there, and iron 3 is there, iron 2 is there, iron 3 is there. So this is in the C4 book, and you need to memorize these. Right, this is the trends for halogens. Halogens are in group 7. So fluorine is a pale yellow gas, chlorine is a green gas. Okay, this is in the book. Bromine, remember that these are all diatomic as well. So bromine is an orangey browny reddish liquid that vaporizes easily. Iodine is a shiny grey-black crystalline solid that sublimes to form a purple vapor. Going down the halogens, density increases and the melting points and boiling points increase. How do you explain the trend in reactivity? The halogens have similar chemical properties because all their atoms have 7 electrons in their outer shell. They gain an electron in reactions completing their outer shell and forming ions with a single negative charge, so that's -1. The general ionic equation models the change below. So X stands for the group 7 diatomic molecule. When that gains 2 electrons, that becomes 2 separate ions. The easier it is for a halogen atom to gain an outer electron, the more reactive the element is. Now, in group 7, the fluorine is more reactive because it only needs 1 electron in the outer shell. However, if you go further down the group, the protons are more attracted to the electrons. And so it is a lot harder to gain that extra electron. So this is the opposite trend to group 1 elements, because in group 1, the atom, the outer electron is further away from the nucleus, and so therefore it is weaker, because there's only one single electron that's further away. But for group 7, it's nearly completely full, and so therefore the nucleus is attracting the electrons. For example, chlorine is more reactive than iodine because its atoms gain an outer electron more easily than iodine atoms do. Right, why are the noble gases so unreactive? Because it has a full outer shell. Because it has a full outer shell, it won't combine with anything. They have no tendency to lose or gain electrons to form ions. They don't share. They prefer to be solitary entities. As a result, the noble gases are very unreactive. So because they're very full, it has a full shell, it doesn't need to combine, doesn't need to share, doesn't need to lose or gain electrons. And so because the noble gases, the ones in group 0, because they have full shells and they like to be solitary, the noble gases are monatomic, unlike the group 7s, because the group 7s are diatomic. For the noble gases, they like to be alone, because they already have full shells, they are monatomic. So they exist as single atoms with very weak forces of attraction between them. These forces are easily overcome by heating. This gives the noble gases very low boiling points. Going down the group, the attractive forces between atoms get stronger, the boiling point increases. The noble gases have very low densities. This is because the atoms are far apart in the gas state, so there is very little mass in a given volume. As you go down group 0, the density increases. How do you detect carbonate atoms? This was not done earlier today. So hydrogen ions form dilute acids. Now remember, acids have H+ ions. Alkalis have hydroxide ions. So the more hydrogen ions you have, the more acidic it is. Hydrogen ions from dilute acids react with carbonate atoms to produce carbon dioxide and water. This forms the basis of a simple laboratory test to detect carbonate atoms. It works whether the carbonate compound is in the solid state or in a solution. This is useful because most carbonates, such as magnesium carbonate, I just repeated myself right. So such as magnesium carbonate, MgCO3, are insoluble. You detect carbonate atoms. What do? You add hydrochloric acid. If for a positive test, bubbles of gas will be produced. Now, to confirm that it is indeed carbon dioxide, you would put the carbon dioxide through lime water. You could use dilute nitric acid, but dilute hydrochloric acid is used more often. Right, so these are the flame test colors for the metal ions in the book. Hydroxide precipitate color. This is the same as this one. Yes.